So I understand the last few lectures have not been the most exhilarating content in the world. We're kind of stuck in the weeds right now of cranking out some definitions for calculating fugacities for mixtures. Once we can get out of that, then we can actually start doing some applications. So I promise it'll be a little bit more fun after fall break. So we're going to have a bit more definitions, but I'll try and pepper in some interesting topics of discussion in between so we don't lose our minds. So as a recap, I like doing these recaps, especially when we get really deep into the definitions, because a lot of what we're doing here is all contrived. It's contrived in a particular way to help us solve the problem, but it's contrived nonetheless. It's not intuitive like your fluids course that everyone's looking forward to, right? Where you can visualize the flow, where you can visualize the fluid, and the boundary conditions make sense. What we're talking about now is more or less, how do we get to this term, the partial fugacity of species I in a mixture? That's really what we're trying to get at. Because this is the property of a fluid that is held constant across all phases. So if we can find a way to calculate this property through some manipulation of our thermodynamic variables, then we can solve ultimately all phase equilibrium. But what we need to do is we need to talk about, how do we calculate this for a gas? How do we calculate this for a liquid? How do we calculate this for a solid? How do we calculate this for a real fluid? How do we calculate it for an ideal fluid? Or what about an ideal mixture of real fluids or a real mixture of real fluids? There's a ton of different combinations that we need to put together to compose a way to calculate these quantities to actually allow us to solve vapor-liquid equilibrium, liquid-liquid equilibrium, and so on. So if we were to build kind of a graph of realness, I suppose, real to simple, right, going down on this axis, and then going across over here, we have a pure fluid versus a mixture. This kind of breaks down some pathways that we have to talk about. So a real pure fluid, nomenclature-wise, right, we write it here, we can put a little subscript I, knowing that we're eventually going to make this into a mixture. This is the real property of a real fluid. So this is a real fluid property. Now if we were to take our fluid, a real fluid, and put it into a real mixture, we would then get partial molar properties that are a function of temperature, pressure, and composition. So this is a real mixture of real fluids. This is what actually happens in real life. This is the property we're ultimately trying to calculate, because if we do this approach for partial molar Gibbs, then that gives us an entryway into calculating the fugacity. Yes?
Just a really simple question, maybe I missed this, but what is the X underbar supposed to be?
That is a shorthand notation for composition.
Is that like X of I, or?
I think it's the notation the book uses, and it seemed clever enough to me. So the idea here is that if I have a fluid consisting of, let's say, 5 or 6 components, I would have X of 1, X of 2, X of 3, X of 4, and so on and so forth, right, for a real mixture of complex systems. So instead of saying that this property is a function of X1, X2, X3, X4, X5, we just say it's a function of the composition, so we draw the X underbar. Just a shorthand notation to say that this property is a function of not only the temperature and pressure, which we would expect it to be, but also a function of the composition of the entire system.
Okay, so if you were to not use that X underbar, you could write X1, X2, X3, X4.
Exactly.
So, okay.
But I prefer not to.
Yeah.
So for an example, my research is associated with, to a large part, looking at petroleum samples, and petroleum samples are very, very complex. What this is effectively saying here is that if I pull anything out of this system for a real fundamental approach, I'm changing the properties of everything, right? It's all a cascading effect. So if I have a mixture of light hydrocarbons and heavy hydrocarbons, like it starts off with in crude oil, if I pull off some of the light material, that's going to change how the heavy stuff behaves. Potentially, right? We don't know without any prior assumptions what's going to happen. And so that's why everything is a function of everything. So when you put it into a mixture, that's when things get extremely complex. Because if I'm trying to calculate the partial fugacity here of species I, that partial fugacity is a function of species I, J, K, L, M, N. Everything is a function of everything. And that's why multi-component systems with multi-phase gets very hairy really quickly. So in large part, it's unpleasant. So what we try and do instead is lump for really complex mixtures, anything more than 2 or 3 components. Typically, you'll try and lump them into pseudo-components. But when it gets to be extremely heterogeneous, then you'd be really good at numerical solutions. Okay, all right. So this is the real system. This is our goal. That's what we're trying to get to. Now we can make an approximation of this step if we come down and we write theta over bar of I for an ideal mixture. Even though it's ideal, it is still a function of the composition, temperature, and pressure. So this is an ideal mixture of real fluids. So an example of what would be an ideal mixture of real fluids would be if I take 2 liquids and I mix them together. Let's say I take 1 propanol and mix it with isopropanol, right? That would be the case of, this is isopropanol and 1 propanol, 1, 2, 3 OH, right? Yeah, they're pretty similar. We would expect them to behave somewhat as an ideal mixture. The only difference is the isotopic arrangement. But the real reason why these are an ideal mixture of real fluids is because, of course, the ideal gas law does not predict that liquids even exist. So the mere fact that they're liquids means that they're going to be, to the most part, a real fluid. We'll have to either rely on an equation of state or measurement property information to know what are the conditions of the liquid isopropanol. But we should have an equation of state that would be reasonably accurate to predict something as relatively straightforward as isopropanol. That would be an example of an ideal mixture of real fluids. Now, even if it's not an ideal mixture, we can always still use that as a starting point for approximation. Now, if we go down and we take a big step in approximation, if we don't have a real fluid, we have an ideal fluid, and the best ideal fluid that we're going to have is going to be, of course, an ideal gas law. So we can have the pure species properties of an ideal gas, and these are going to be functions of temperature and pressure. Right? For internal energy and enthalpy, they're only a function of temperature, but for entropy, it's also a function of pressure as well. And this would be an ideal gas. Now, we could really stop off anyway along the way down here. We could say this is a virial equation, or a virial fluid, or a van der Waals equation, or an SRK equation, or maybe some really specific, field-dependent equation of state that maybe is housed in the libraries of Dow and DuPont. Right? They might have some very specialized equations of state for particular fluids of interest of theirs. And then the next step over here, if we mix ideal gases, we would get the theta over bar, but in this case, ideal gas mixture, temperature, pressure, composition. This is an ideal gas mixture. Now, as a general hand-wavy approximation, so if we're dealing with gases, we're probably pretty much okay if we were to use a decent equation of state. Gases are relatively low density, and so if we have a little bit of inaccuracy on how 2 particles interact, there's just not that many particle-particle interactions to really significantly throw off the accuracy of the simulation, or the calculation rather. When we get to liquids, then we have tremendously higher quantities of interactions. In that case, it would be more difficult. So for liquids, pure liquid properties are okay if we're dealing with something that's relatively simple. Now, what we quantify as relatively simple is something like benzene or toluene or normal alkanes. Maybe isopropanol would be sufficient. Once we start to get to something that is either high molecular weight or strongly polar, even something like water, the only reason why water is okay is because we have very specialized equations of state for water properties. But in general, water would almost not even be considered a simple component. The polarity of it is so high and the interactions and the structure of the fluid is so high that it gets us really difficult to represent it with an equation of state. Now remember that these cubic equations of state, they're not real representations of how the fluid behaves. It's clever arithmetic, and it allows us to represent the fluids based on their bulk properties, but they don't actually represent anything that's actually going on in the molecular length scale. So that's one of the difficulties. And for mixtures, so an equation of state is okay if the mixture is what I would call very, very simple. Right, we're talking strictly hydrocarbons, maybe some polar groups, but nothing that's really strong. Hydrogen bonding is probably a no-no, unless it's a really, really well-studied system. If it doesn't fall into these categories, then we kind of have to fall into the realm of using activity coefficients. That's what we're going to talk about right now. So that's a recap of all of the grab bag of options. So when we're posed with a question, whether it's a homework problem or something associated with the research or ultimately something in your career long term, if we're trying to estimate, and the emphasis of this class is going to be on fluid phase equilibrium, right? We want to know what the partial molar fugacity is, the partial fugacity, or the partial molar Gibbs. That's our goal, to calculate the phase behavior for separations, for crystallization, precipitation, whatever the case is. This is our ultimate goal. But we have a grab bag of options to get us to this point, and it all depends on where do we want to step off in terms of the simplicity. This, of course, obviously, if we just go into the lab and measure the conditions, we're going to be directly measuring what the phase behavior is, and then back calculating, for example, what the activity coefficient could be potentially. So a lot of different possibilities. Is it a real fluid? Is it an ideal fluid? Is it an ideal mixture? Is it a real mixture? Is it an ideal gas mixture? All right. It's a little crooked. You might straighten that out a little bit. Could you tip it just a little that way? I think I bumped it or something. A little bit more. Perfect, thank you. All right. So, in order to define the activity coefficient, and this, who remembers what an activity coefficient is?
You use it with Raoult's law.
You can use it with Raoult's law. So the exact details of what an activity coefficient is has been lost to time, it appears. So in order to get there, we need to define something called an excess property. Now the excess property, again, we're going to denote this with a little EX. So this is an underbar, no subscript, meaning that this is the total property for a mixture, but in this case we're going to define something called an excess property. 3 lines, meaning we're defining it. This is the difference between the delta of mixing of some system. And of course, these are all function of temperature, pressure, and composition. Temperature, pressure, composition, minus the delta of mixing for an ideal mixture. Let me put this in the same spot, delta mix. So it's a little bit different than just the change in mixing. Right, so the change in mixing was previously defined as the pure versus the mixture. The excess property is defined as the real mixture properties of the delta of mixing versus the ideal mixture properties of the delta of mixing. Right, so it's a little bit different of a definition. So for enthalpy, internal energy, and volume, the excess of mixing, let's see, theta under bar excess is just equal to the delta mixing of the property. And one other note is we can also write this here as the summation, and this will highlight the difference. So the excess property is the partial molar property of the fluid minus what its partial molar property would be as an ideal mixture. And this is distinct from the volume, sorry, the mixture property changes for just the delta of mixing. Right, this is the pure species, this is the partial molar species quantity. Okay? Right, so for enthalpy, internal energy, and specific volume, there's no difference. Excess property is the same thing as the mixing. So if I do a calorimetry experiment, I mix two things together and energy is released, that means I have negative delta H of mixing, which is the same thing as having a negative excess enthalpy. For entropy, Gibbs, and Helmholtz, they all have entropy in it, and we know from previous discussions that the change in mixing, even for an ideal mixing, is non-trivial for an ideal gas. We're always generating entropy when we mix two fluids together because we're giving each of the two fluids more volume to work around with. So even in an ideal mixture scenario, your entropy is always going to increase. So that means we have to do a little bit of extra special consideration for these ones. So for the entropy, and it's a sort of a fun little, you get an SEX there. Giggle about that. Is the actual fluid entropy of mixing minus the ideal delta change of mixing. In this case, the minus turns into a plus in the case of entropy. So in this case here, if we were to look at this here, this is, so the delta S of mixing for an ideal mixture is minus R summation xi ln xi for entropy. So then for Gibbs and Helmholtz, it's going to be a very similar look. Excess delta mix of the Gibbs of the actual system. In this case, it's going to be a minus RT. This makes sense, right? Because Gibbs is, H minus TS. So you have we're adding the T, and then the minus turns into a plus. Basically the same thing. And then exactly the same for the Helmholtz, but I'll just write it out for completeness. Why do we bother with all of this? Because if we go back to our chart of difficult versus simple fluids, or real versus simple to calculate, we're whiz kids with ideal gases. I know that I can throw any ideal gas state change to you guys and you can calculate it. Likewise, if you have an ideal gas mixture, it's very trivial to calculate what the properties of an ideal gas is in a mixture. The only one that's even remotely complicated is the entropy. For the other ones, it's exactly the same. So if I'm going to create a textbook of properties of real fluids and guidelines of how to calculate those properties, I'm not going to waste my valuable real estate in that textbook re-explaining how to calculate ideal gas property changes. Instead, the only information that we really care about in terms of phase equilibrium is in telling us how does our real system deviate from the ideal gas mixture system. So the important piece of information to tabulate is this one right here, is the excess Gibbs free energy. Not the Gibbs free energy, the excess. Because it is trivial to calculate the properties of an ideal gas mixture. So instead of having a weird xi natural log of xi function in every single thing that I tabulate in a textbook, I'm going to ignore that, get rid of it, and only focus on the interesting characteristics of how it really deviates from that behavior. And this is one of the implicit complexities built into thermodynamics. Again, we're teaching the system. Why are we teaching the system? Because it's so much easier to only worry about how it deviates from ideal behavior. So before you could even get your foot in the door to calculate anything associated with thermodynamics, you already have to have some degree of a mastery of the basics. Right? So that's why even sort of simple thermodynamic calculations can seem very daunting, because the assumption in all of this is always that you know what you're doing, at least a little bit to start off with. And so the nomenclature and the language and the procedures are all built upon this complexity. So that allows us to get closer and closer to our activity coefficient definition. So what we showed previously is that based on the way that we formulate the partial molar properties, we can more or less take all the relationships that hold for pure species properties and then hold them true for partial properties as well. So in that sense, we can also write that we have a partial excess Gibbs free energy. It can effectively be defined, or we can show that this is a valid point as well. Actually, let's get rid of the definition. This is supported by just this definition down here. The real partial Gibbs of species I in a mixture minus the partial molar Gibbs as if it were in an ideal mixture. So what we're going to do is we're going to play around with this a little bit to get it into a form that looks something like the fugacity. So we're going to add and subtract the Gibbs of an ideal gas mixture to this equation. The idea here is that we're going to try and set up two different differences, and then we can get it to two different forms of fugacity. So that means we can rewrite this here. All I did is I added and subtracted Gibbs of an ideal gas mixture. So this is the Gibbs of the pure species for a real, Gibbs, partial Gibbs of species I in a real fluid mixture minus an ideal gas fluid mixture. So we're starting off with ideal gases, then we're mixing those ideal gases. Same thing here. And this one here, we're starting off with a real pure fluid, but we're mixing it ideally. So this one expression has all of the nomenclature built into one. Now, if we substitute in our expressions for these two terms, right, because we effectively already have our property information here for ideal mixtures, especially ideal gas mixtures. This one will keep the same. And this one over here will expand on. We'll substitute in these two expressions here. marker, different color to annotate this a little bit. So this is there. And this chunk here is there. And let's analyze this just for 1 second to make sure we haven't made any mistakes. Partial Gibbs of an ideal gas mixture. We're starting off with, oops, I did screw this up actually. We're starting off with a pure ideal gas, right? That's the underbar, but still subscript I. And then we're adding in the contribution of the ideal mixing. Likewise here, we have the Gibbs of a pure real fluid, right? No ideal gas mixture, none of that. We have an underbar, and then we're adding in the contribution of the mixing for an ideal mixture property, right? Ideal mixture, ideal mixture. So we have, thankfully, a couple things cancel out. This cancels with this. And our final expression, not our final. These look familiar. Hopefully they should look a little bit familiar. What we're talking about is the Gibbs of a species in a mixture minus the Gibbs of an ideal gas mixture. This one here is the negative, right? But effectively we're looking at the difference between the Gibbs of a pure species minus the Gibbs of an ideal gas. What does that lead us in the direction of? Fugacity, right? This is effectively the negative of the definition of fugacity. And this one's a little bit different, but it's effectively the fugacity, the partial fugacity definition. So we're substituting in our fugacity definitions. All we're doing is substituting our fugacity definitions. And then we can rewrite that our partial excess Gibbs, again, our nomenclature, we're getting really deep in the weeds here a little bit. And there's so many different ways we can write these things out. I'm giving a few of them here. All right. So these pressures end up canceling out using logarithm properties. So what we're looking at, in a rough sense, is that the partial molar excess Gibbs, which, believe it or not, is the quantity that we're interested in. This is telling us how does species I behave in a mixture as a relative comparison to how it would behave in an ideal mixture. In an ideal mixture, everything is miscible in everything. Right? We talked about that a little bit, how when I mix two things together, I gain a tremendous amount of entropy, no matter what, just by default. But when I mix things together, ideally, I have no energy change that's released. I have no volume change. I have no delta H, I have no delta U, I have no delta V of mixing in an ideal mixture. So the only thing that happens in an ideal mixture is that two fluids mix together. So if there's two fluids that don't mix together, and we do have a phase transition occurring, which in my mind is the interesting part of thermodynamics, right? If everything just mixed together, then everything would melt into one big pot. So it's good that the floor doesn't dissolve into the table and vice versa. So all of the interesting information contained with phase transitions and fluid phase equilibrium behavior is contained in how does the Gibbs free energy differ from that ideal mixture. So we need to have a strong repulsive interaction between molecules to overcome the entropy that's being gained when the two fluids are mixed together ideally. So this is ultimately the value of interest that we're really interested in. But we've gone on quite a long journey to get here, right? So starting at the beginning of class, all we had was entropy, internal energy, and volume. Then we defined the Gibbs. Then we defined the partial molar Gibbs. Then we defined Gibbs of mixing. Then we defined the excess Gibbs of mixing to get us to this point here. And then we're going to define the partial fugacity, which is a more convenient way to calculate this process. So even when you crack open any thermo textbook and attempt to solve a problem, you have to remember that journey that we took to get all the way over here, otherwise it's going to seem like a jumbled mess. And I think that's the problem with most people when they approach thermodynamics, is that in order to even get access to using these values, you have to already have a large body of knowledge. So what we're looking at here then is effectively partial fugacity would be how the system actually behaves in the mixture relative to that pure fluid fugacity. That's why we have fugacity of species I as opposed to the system pressure like we had in our first definition of fugacity, right? Because we're talking about, for the excess sense, not relative to the pure species, not relative to an ideal gas species, but relative to a real fluid and an ideal mixture, right? So this xi mole fraction times by the fugacity, this is the case of the fugacity if it's an ideal mixture. So if the xi times by the fugacity mole fraction times the fugacity is equal to partial fugacity, this is 0 and excess is 0. Or this is 1. 1, natural log of 1 is 0, that means you have nothing here going on with the excess Gibbs. Does that sound reasonable to everyone? And then we can also calculate that using an equation of state. In this case here though, if we compare this to our definition of Gibbs, fugacity, this is not the ideal gas law. You can't substitute it in. Now, what this allows us to do is we can finally define the activity coefficient. We represent the activity coefficient as gamma. This gamma of I is the activity coefficient of species I. And we define it, so it is a function of temperature, pressure, and composition. We define it as, like so. Typically, I'll put little L's here. Typically, we only use it for liquids. So there are a couple of other ways we can write this to sort of discuss it a little bit. A couple of different ways we can write out the activity coefficient. They're all just algebraic manipulations, so nothing new, just different ways to talk about it. Okay, so activity coefficient, the information it contains, I'll let everyone give a second to write it down. Actually, one more thing on the board here. Squeeze it in. Sorry for your notes. We also have a equivalent relationship for the Gibbs-Duhem expression on how activity coefficients between species have to be related. This is for a binary system. All right, so what the activity coefficient represents is the activity coefficient tells us how much free energy is deviating between an ideal mixture system. So what we're looking at here is the fugacity of a pure species, not an ideal gas, compared to the partial fugacity of that same species in the liquid phase. So how we oftentimes apply it is from this relationship here. We are looking for, in the case of vapor-liquid equilibrium, we need an expression of how to calculate the partial fugacity of species I in the vapor phase, because that has to be exactly equal to the partial fugacity of the species I in the liquid phase. For the gas phase, we have a lot of convenient ways to calculate it, and we'll talk a little bit more about that on Friday if everyone has attention available. But ultimately, for the liquid phase, what we care about, right, is how does that change when I mix the fluid. So here is my pure liquid fugacity. This is what we calculated using the van der Waals equation of state. Here is an activity coefficient that tells us how my system properties change when I mix them, and then this x just kind of factors into the whole problem. So when we talked about the activity coefficient, the one term that I heard was Raoult's law. Let's talk about Raoult's law for 1 second.
I just have a little bit of
Yes.
question on that formula right down there.
Mhm.
You say it's a pure fugacity, that term at the end.
Yes, this is the fugacity of a pure fluid.
Okay, but it's F sub I, so that's a pure.
Pure fluid I. The
Okay.
reason we don't do an underbar is because it's not a molar property.
Okay,
Yeah.
right. Okay.
Because the fugacity has units of pressure, which is an intensive property, so fugacity is an intensive variable. So we can't have doesn't change when I change the amount.
Right.
And then the activity coefficient is directly related to the partial molar excess Gibbs. So Raoult's law. What is Raoult's law used for? What can I calculate with Raoult's law?
Vapor-liquid equilibrium.
Vapor-liquid equilibrium. What is Raoult's law?
Why?
This is Raoult's law. Now there's also a modified form of Raoult's law where we toss in an activity coefficient. Or we could say this is equal to, right, that's a modified form of Raoult's law. So the question is, how do we get from here to Raoult's law? So with Raoult's law, we have our starting point for phase equilibrium is our partial fugacity of species I in the vapor phase is going to have to equal to the partial fugacity of species I in the liquid phase. So that tells us that this expression is equivalent to that, and that this expression is an approximation, right? So let's walk through in our heads a few of the approximations that we're talking about here. We'll go into more depth with vapor-liquid equilibrium, but I want to give everyone a little bit of a preview. So how do I go from this complex expression of partial fugacity, we're involving excess Gibbs free energy, to something as simple as the mole fraction times by the system pressure? What's an approximation that's baked into Raoult's law? The vapor phase is an ideal gas, right? So if the vapor phase is an ideal gas, that tells me that the fugacity of the vapor is just equal to the system pressure. And that also tells us that the partial fugacity is just a scaled version of the pressure, because this is an ideal mixture. We have an ideal mixture of ideal gases. That satisfies the vapor phase. Now, if we talk about the liquid phase, what are some approximations baked into this already? right? We've already stated one of them, but it's an ideal gas. So what happens, what's the fugacity of a saturated ideal gas?
System pressure.
System pressure, which is also going to have to be the saturation pressure. So in that case, then, the fugacity of the pure liquid species is simply equal to its saturation pressure. And this is all the direct consequence of the ideal gas. Now, in the case here, if activity coefficient is equal to 1, that means that the partial fugacity is just equal to the scaled form of the fugacity. So all of these are baked into Raoult's law. And we'll be going over this again in significant and tremendous detail. So there is light at the end of the tunnel. That's all I'm saying. So Raoult's law, right, you have to recognize all the different approximations that have gone into doing this here. Right, we've assumed no non-ideality in the gas phase, which then transitions into modifying what the fugacity of the pure liquid species is. And then if we assume that the mixture of the liquids is an ideal mixture, then we have Raoult's law. How many systems behave Raoult's law, follow Raoult's law? Based on the number of approximations that we've just covered. Not a whole lot. It's actually not super great. Now, this part is not too bad. If you're dealing with low pressure vapor-liquid equilibrium, which is mostly what we're dealing with. But if we're talking about a really high pressure system, maybe like a cryo distillation column to separate different gases, then this is maybe not super valid. But for the most part, low pressure distillation columns, where you're only doing a temperature swing, gas phase is going to behave reasonably ideally. If not, the mixture properties are going to be ideal mixtures. The pure species properties you'll probably want to predict with an equation of state. Liquids, you almost always need an activity coefficient model. Almost always to get good accurate predictions. All right, so I'm going to leave, we're going to end class with a brief discussion of excess properties, because this is sort of a fun topic that plagued me for quite some time. So, I want to talk about entropy, because entropy, I think, is one of the most interesting concepts in thermodynamics, and it never gets its fair shake. Because it's abstract, and it's somewhat annoying to deal with. So, if I were to look at mixture properties, or in this case excess properties, they're interchangeable. If I'm looking at some particular partial molar property, in fact, let me think about this. Let's actually look at excess properties. So I'm going to draw a positive, potentially and negative. So this will say x1. We're plotting up some excess property. Now, if we're dealing with, let's say, volume, for example. If this is excess volume, and it looks something like this, what does that tell me what happens? So if I mix 1 liter of component 1 and 1 liter of component 2, and this is the curve for my excess volume. And just so we're clear on the same page, the excess is the same as the delta of mixing. So if I were to not plot up the excess, but in this case I were just to plot up the specific volume, I would have a specific volume of fluid 1, I have a specific volume of fluid 2. That dashed line would correspond to the ideal mixture. This is V1, V2. Then I flatten that line, and that becomes the x-axis here. And that would be the results that we're looking at. And so we're plotting up the excess, which is the same thing as the delta of mixing. But from now on, the delta is kind of an antiquated terminology. The excess captures it a little bit better. Right, that's what we're looking at here. So if I mix 1 liter of component 1 and 1 liter of component 2, how does my volume change? Is it 2 liters, more or less?
More.
It's more. Makes sense, okay? Now let's say, for example, I look at enthalpy of mixing. And for the maybe we get something that looks like this, a little bit more different, where the center is not 50-50. Let's say this is excess enthalpy. If I mix a liter of, let's just say a kilogram of component 2 and a kilogram of component 1, what happens? If I do this isothermally, does energy come in or out of the system?
Out of the system.
Out of the system, right? Because if when I mix these two fluids together, let's say at this value here, I'm contributing 0 enthalpy, right? That's according to our reference state. But the enthalpy of the system is much, much lower. So now the fluid has a ton of free energy just floating around and it doesn't know what to do with it. So you either have to pull it out of the system or it goes to heating up the fluid, which is exactly like what we had on the exam questions and on the practice exam. Right? If you mix two things adiabatically, then you have to increase the temperature using the mixture heat capacity to know what the final temperature conditions are. Right? Because I'm giving it 0 enthalpy, but the mixture has negative enthalpy. That means I have a ton of excess just floating around, trying to figure out what to do with it. Now, here's the fun one. Entropy. Now, with entropy, we might think that this is the more conventional approach right here. What if I have two fluids mixed together and I have negative excess entropy? That means that I have less entropy in my system than I would expect to have if I had a strictly ideal mixture. Can someone describe a physical situation where you would expect this to occur? How do I have less entropy than an ideal mixture? So what is an ideal mixture? It's an ideal gas mixture. So what does that physically, intuitively mean? Can someone describe what an ideal gas mixture physically and intuitively is and what negative excess entropy is? Yes?
Ideal gas is that they mix perfectly,
Mm-hmm.
so it's no interaction. So I'm guessing that the entropy being, less.
In the case, it's less. Yeah.
Less is that they don't mix well, so so two fluids that don't dissolve in each other.
Well, so in this case, they will dissolve because it's still a single phase, but you have the right idea. In this case, when you have a negative excess entropy of mixing, it means they don't fully, randomly, completely mix. You'll maybe have some structure in the fluid. Now, this is exactly the case when you mix something called water with hydrotropes. So a hydrotrope is not quite an amphiphile, right? A surfactant is an amphiphile where it's got a hydrophobic head and a hydrophilic tail, right? So for example, you've got a head with a big long tail. Now, if I mix a bunch of these into solution, they'll form a micelle, which is soap. That's how soap basically cleans dirt off. But if you have something like ethanol or isopropanol or butanol, they don't form micelles because they're still a little bit too small, but these are called hydrotropes. So when I mix these with water, they kind of mix, but they kind of don't mix as well. The alkane components of these will kind of self-segregate, not to the extent that they form a micelle, which is a solid body of particles, but rather they just have some short-term fluctuations, right? These normal alkane chains, they like to be by each other, normal alkane chains, a little bit more. The hydrophilic heads, they'll float around with the water pretty well. So the water kind of hangs out with the water, and the alkane chains kind of hang out with the alkane chains, and we do get exactly this observation, negative excess entropy. Okay, now here I'm going with this one. What if I have positive excess entropy? Yes?
Are they reacting together?
No reactions. Nothing of what we're talking about has any reactions. So I don't want to give you the answer. But if someone gives me it'll be super, super large gold star for a concrete description of what positive excess entropy of mixing physically means. This one stumped me for an embarrassingly long time. Anyone have any ideas? What is a system? How would a system physically behave if you have more mixing than ideal mixing, which as we know is 100% random mixing? How do we get more mixing than 100% random mixing. I will tell you this, it's not a trick question, it does exist.
The temperature of the system increase.
Temperature's the same. So they're mixing these two things isothermally.
Can the phase transition be there?
Nope, these are single component systems. Single component system, yeah.
Say spontaneously mixing.
So these are all 100% miscible. So I mix 1 and 2, they'll still dissolve, they'll still mix. If I look at a glass of it, it'll look exactly like a single fluid. I wouldn't be able to tell the difference.
New energy states, like it's not vibrational if it's, and I guess it can acquire this due to mixing.
If you're mixing two things together, you can form complexes potentially that might have different like heat capacities, but this would be not associated with energy modes. That would all be associated with delta H's or delta U's. So entropy is concerned more with configurations. So it wouldn't be anything to do with vibrational modes or additional modes that be activated. But certainly if you do have like excess enthalpy of mixing, that is telling you that the new complex that forms is having different modes. Not necessarily pure component modes, but modes that involve a complex of structures. So for example, if a water molecule wants to vibrate, a sulfuric acid molecule has to vibrate a certain way as well. Okay, so I'm not going to give you the answer, but think about this. It does exist, I promise it exists, and there's a class of compounds that exhibit this kind of characteristic, which I think are really cool. It's not as complicated as you think, but it is sort of a head scratcher for sure. So I'm going to leave it at that. Good luck on your exam on Friday, and I will see you after that if you are all still alive.